Alright, here are the solutions for your Chapter 5 review. Let's see, so here we want to find all critical points, maximums, minimums, inflection points, a cusp or a sharp corner, vertical asymptotes, all that stuff. Intervals of increasing, decreasing, inflection points, and intervals of concave up and down. Alright, so the first one, I think we should try to do this without our calculator. The first derivative of this function, using the product rule, is the derivative of the first, which is 1, times the second. This is my first, this is my second, right? Plus the first times the derivative of the second. Derivative of e to the whatever is e to the whatever times the derivative of what's inside. Okay? I'm going to clean that up some because I know I would like to try to factor this. So let's see, this looks like it's going to be minus x squared, so I have e minus x squared over 2. Factor that out, and then I have 1 minus x squared. And of course that factors into 1 minus x, 1 plus x. Okay? While I'm at it, how to find the second derivative? I'm going to find the derivative of it. Let's see which form would be the best one for me to deal with. I guess I could use this. You can take the derivative of any of these versions of it. I think this one might be the easiest. So again, using the product rule, I have the derivative of the first, which is minus x e to the minus x squared over 2. That's the derivative of that. We already found that right there. Times the second plus the first times the derivative of the second. Right? Right. And if I factor out the e to the minus x squared over 2, and what I have left behind is a minus x times this. That's a minus x and a plus x cubed, and then a minus 2x. So if you'll trust me to skip a little algebra there, that's going to look like that. Right? Just check that again. So factoring out the factoring out e to the minus x squared over 2, I have this left behind and this left behind. So that's minus x plus x cubed. And then I also have minus 2x here. So I'm confident that that's good. And then I could further factor this into x times x squared minus 3. Okay, so I'm going to do all my answers here on one big number line, one big sign chart for you, okay? And it's unlikely that you're going to see one problem where you have to do this much information. This is just practice for us, so I think it's okay to lay things out this way. I'm going to do a sign chart kind of like we do the velocity acceleration when we're looking for intervals of speeding up and slowing down. I put f prime on the top, f double prime on the bottom. So places where the derivative is 0, the derivative is 0 at 1 and negative 1. Sign chart. This is always positive, and this here, if you check the signs in between here, or you consider that this is a downward opening parabola, so it must go negative, positive, negative, one way or another. You should get signs like that. And then your second derivative, we have zeros at 0 and plus or minus the square root of 3. and this is a cubic function, so it's going to go negative, positive, negative, positive. You can try, plug in numbers there, that's fine if you don't like that shortcut that I'm using there. So we're going to go negative, positive, negative, positive. Right? Okay, so just running through these things briefly. Intervals of increasing and decreasing, well, here they are. From negative infinity to negative 1, it's decreasing, and then it's increasing from negative 1 to 1, and then decreasing again from 1 to infinity. Notice I'm looking at the first derivative. Intervals of increasing and decreasing, those are questions about f prime. Right? And I guess I skipped A, so maximums and minimums and all that stuff. So if this is going from decreasing to increasing, then this must be a minimum. And if this is going from increasing to decreasing, this must be a maximum. We're doing this everywhere. We're not doing a closed interval, so I'm not checking endpoints here because there are no endpoints to check, right? Let's see. Inflection points. Those are places where the second derivative changes sign. Well, there's 3 of them. It does actually change sign here, here, and here. So at negative, square root of 3, at 0, and square root of 3. Those all are places where it genuinely does change sign. Watch out for setting the second derivative equal to 0 and not changing and having signs not change. You do have to confirm that there's a sign change for it to be an inflection point. All right, and intervals concave up and down, so concave down, concave up, concave down, concave up. All right, that was fun. Now, this one, I'm going to do the same thing, but I'm going to generate this pretty much entirely with my calculator. So there's a couple ways you could go here. You could find the derivative of this by hand and then graph that, or you could, if you're going to use your calculator, then you could graph the derivative using your calculator, and I do want you to know how to do that. So I'm going to go for that option. In my y equals menu, I want to graph the derivative. That's math 8. If you have math print, you're going to have that fancy looking thing here. I need to put the top of it in parentheses. If you have math print, you should take advantage of your little fraction thing you can do there. Minus x plus 1 over parentheses x squared minus 4. So there's my function, comma x, and then a comma x again. And those are the x's that you're putting in, like the little dx on the bottom and the little x over on the side for you math print folks. And for us old school ones, that's how we have to enter it there. All right. Now, let's see. I guess I'll look at this in the standard window, so I'm going to do zoom 6. That's my standard window. It's a little slow, graphing derivatives. All right. So, let's take another look at what we got here. This is a graph of the derivative of this function. So how do I find the places where the derivative's equal to 0? Well, they're the places where the derivative's equal to 0. So let's see. I'm going to find those zeros. There's one over there. That one looks like it's in between, let's see, -1, -2, -3. It's between -4 and -2, right? So instead of playing with the cursor, that's annoying, I'm just going to type in left bound -4, right bound -2. Let's see if you'll know if you got a good interval there. Oh no, you know what, I picked -2, that's on the vertical asymptote. Oh, but it still found it, look at that. Good job, calculator. So it did find it. You can see the cursor shows up there. So that's at -3.157. College Board wants 3 decimal places. -3.157. Right? next one. So I can calculate that 0 here. It looks like there's one in between -1 and 0. So -1 and 0. And we'll see, yep. So at negative 0.721. Now I'm going to fill in the signs as I go. Over here, on this side, we have positive. And then here I have negative. But there's also, I think I should probably put in here, this is, there's a vertical asymptote here at -2. So it goes from decreasing on one side and then it's still negative on the other side of that. But it would be kind of misleading to just put a big negative in there. That would imply that it's negative also at -2. So I think I want to draw that vertical asymptote in there just to remind myself that it's there. Then I got another 0 over here. It looks like, well, my cursor's close enough. I guess I could just find that one. Left bound, right bound. .525, and it's not very positive, but it's above the axis there. You could zoom in on that if you didn't believe it. And then there's another asymptote, crosses into the negatives again. Another asymptote. This is at x equals -2. This one's at x equals 2, and comes up again. More negatives, and then it looks like it crosses there. Last 0 that I need to find. 1, 2. So let's say between 3 and 5 anyway. So second calculate 0, left bound between 3 and 5, it looks like. There it is, 3.353. That's here, 3.353, and then it's positive again after that. Whew, that was a lot of work, right? Okay, now the inflection points. To find the inflection points, well, that's where the slope of the derivative changes sign. In other words, where this goes from increasing to decreasing. So if this is decreasing, then the second derivative is negative. This is going down, so the second derivative is negative. And then here it's going up to whatever that point is there. It's going up, then it's going down, and then it's going up again on this side of the asymptote. So the only thing I'm missing here is it looks like I have a spot in here, that little maximum. So I'm going to find that. Second, calculate that maximum. Looks like it's between -1 and 1. Don't assume that it's at 0. Because it ain't. -0.112. And that looks like it's really the only inflection point here, right? You could be suspicious. I don't think it's an issue with this function, but we could check. That's awfully flat there. So it's possible it's so flat, like there could be like a maximum in there. And we could check that by making the y values go from only like 0 to 2. Let's just take a quick look at that. If I did 0 to 2 and just zoom in on that band of it from 0 to 2. But it looks like we're good. It looks like it's only decreasing. That's what we thought. There's that little maximum. So I think we're good. Okay, so all the stuff, all the information to extract from here. Intervals of increasing and decreasing. So it's increasing and then it's decreasing, then decreasing. You can't say it's decreasing from here to here because it doesn't exist at -2. You got to say it's decreasing from here to -2 and then again from -2 to this, right? Because it's not defined at 2 or -2. then increasing, decreasing, decreasing, increasing. Concave down, concave up, concave down, concave up. Right? This would be a minimum. This would be a maximum, right? Increasing, decreasing, maximum, minimum, maximum. Sorry, did that the wrong way, didn't I? And then minimum. This is the only inflection point. You can see that the concavity does change here on either side of this asymptote, but you can't say that there's an inflection point there because there's no point on the original function. Like 2 and -2, you can't plug in the first place. Does it change concavity? Sure, as it crosses that, but there's not an inflection point there because there's not a point. So here, there's your only inflection point. All right, that's some pretty heavy calculator work there. Let's see if we're going to break this up or not. Let's do number 3, and then maybe we'll separate into another video after that. All right, so here's a table with a whole bunch of stuff. I've got some x values at 0, 1, 2, 3, 4, 5, 6. I've got a couple of points here that I could plot, and then I have information about derivatives, and I have information about concavity. And we want to try to make some kind of sketch of this. So let's go ahead and start by by plotting, do or do not, there's no try. So by just plotting the points that we have. So 0, 0, 1, I don't know what, 2, 6, 2, 1, 2, 3, 4, 5, 6, so 2, 6, about here, 3, 3, 4, 0, 5, don't know, 6, 4, 6, looks about right, 1, 2, 3, 4, 5, 6, yeah. Okay, so those are the points that I know. Let's see, what else do we know? We know at 0 the derivative is positive, so that means it's increasing there, so I'm just going to kind of draw a little line through there. On the interval in between 0 and 1, it's always increasing, and then when x is equal to 1, the derivative is 0. So somehow it's going to like flatten out. It's increasing, but then the derivative is going to be 0. So somewhere, wherever it gets to here, it's going to flatten out, right? That's what that's telling me there. Then it's going to increase again, right? Increase again, and at 6, the derivative and the second derivative are undefined. Now the function was defined there, so that can mean one of two things. Either the tangent line is vertical for a second, which doesn't look likely because it looks like it's coming back down, or there's a sharp corner there. So I think probably there must be a sharp corner here because that derivative is undefined there. Now after that, between 2 and 3, now the derivative is negative. So I'm coming back down this way. And then at 3, 3, the derivative is negative again, decreasing there. In between 3 and 4, it's decreasing still, right? Headed down to that point. At 4, it looks like the derivative is 0, so I have a horizontal tangent line, and also this is positive, so second derivative test, if this is 0 and this is positive, so horizontal tangent and concave up means it must be a little minimum like that. And then they're both positive, so it's increasing and concave up until it gets to 5, where I have a positive derivative, but I have an inflection point, right? So it's still increasing, but I went from concave up to concave down. So concave up to concave down. There's got to be some kind of inflection point there, from bending up to bending down. And then in between 5 and 6, sorry, that's what we just did. And then at 6, it's increasing, so it just keeps doing the same thing there, right? increasing concave down. All right, so let's see if we can kind of sketch our way through there. Here, on my way from 0 to 1, I'm positive. I'm increasing concave down. So it's increasing but concave down. Increasing but bending down. And then after that, here, I'm increasing but now I'm concave up. So increasing, concave up. And right there, I had a slope of 0, right? So it flattened out there. So kind of like the cubic type function thing. And it came into this point. I have a sharp corner here, right? That's my undefined stuff. And then from 2 to 3, I'm decreasing concave down. So that means I'm decreasing and bending downward. So decreasing, bending down, and I knew that it was going to be decreasing there, right? So I put my little line in there. And then from 3 to 4, I'm decreasing but concave up. So I'm decreasing but bending upward. So it starts to bend up. This would be an inflection point here. This is also an inflection point. And then from 4 to 5, I'm increasing and concave up. Increasing and concave up. And then there's an inflection point here. And now I'm increasing but concave down. So there's another inflection point. So my arrows here are pointing at the inflection points. So it looks something like that. I think it's a good exercise in interpreting, thinking about what all these things mean. Again, I would be surprised if you saw a problem exactly like that, but I think there's a lot of good thinking in working through that and understanding what's going on. And that's 22 minutes of 3 problems. That's enough for the first video, I think.